Hey guys, Brendan Productions here, and welcome to my second tutorial on hashing. Now, just a word of warning, I have a feeling that this series is going to quickly get away from hashing and start focusing more on computer security topics. So if that's your interest, follow this tutorial series. If it's not your interest, you could still casually watch, but just know that that's probably the direction that these are going to be heading. All right, I just got my coffee, so let's go ahead and start with the video. So in the last hashing tutorial, we talked about what hash functions are, which are basically a non-reversible, collision-resistant mapping of any string to a fixed length of a certain subset. So I also mentioned that this is a great way to store passwords. Indeed, it's non-reversible. So go ahead, store your passwords this way. And in this video, I'll be demonstrating just that. Mainly, I'll be demonstrating the drawbacks of this and how you can crack this particular setup. So, I've written a few programs to help with this tutorial. Don't be overwhelmed by the programs, don't be distracted by them. They're just to aid in demonstration. So, as I mentioned last time, hash functions map the contents of a string to a fixed length string. So, you can imagine executing the hash function MD5 on a password. It gives you this hash, right? And there is no way to take this particular hash string and revert it back to the word password. There's simply no way. It's non-reversible. So, if we're trying to store users' passwords, the most obvious answer is to, well, when they first register, take the password that they type, hash it, and store it in the database. Then, every time they're trying to log in, hash their password that they type and compare it with the one stored in the database. In this way, if anybody steals the database, which is, highly likely, if anybody steals the database, they don't get any passwords, right? They won't be able to log into the services because they can't see the passwords, and they don't know these users' other passwords, right? Because chances are users have signed up for many websites with the same password. So hackers want to grab these passwords and then use them for other more important websites like banks, etc. So when we keep our passwords hashed, we don't give the hackers a way to directly access these passwords so they can log into users' bank accounts, etc. So let's go ahead and give this a shot. So I have this text file open called passwords.txt, which will serve as our passwords database. And I also have this program called register, which will simulate registering for a service. So we're going to register with a username and password. So I'm going to use the username Brandon and the very strong password, password. Right? And this register program gives us the hash just so we can see. And our passwords database actually now has a good mapping of username to password here. So this is what our password database would look like. So then every time somebody tries to log in using the username Brandon, their password that they type in will be hashed and compared to the hash stored in the database. We can also register someone else. Let's register Joe with the password whodunit. Right? Same setup. We load the database, and now we have, just ignore these $J's here, Control J characters. But now we have this username named Joe and his hash of his password. Right, so this seems pretty secure. If somebody were to intercept this database, which is the most worrisome thing, right? You can easily intercept someone's database by getting onto their system somehow, by exploiting a vulnerability, things of that nature, by stealing hard drives, etc. And more importantly, you can also sniff network traffic as well, right? So you can actually see the characters of the password being transferred over the internet. But since we encrypted the password, since we hashed the password before we sent it over the internet, even the person on the internet is only going to see the hash password. They're not going to see the real thing. So we can go ahead and test this out by using this login.py program I created. So we're going to log in as Brandon with the password. And we've successfully logged in, right? Because the login hashes the password and compares it to the database. So this is a great way to store passwords. However, there is definitely a naive side of it. Now, if I was trying to steal a bunch of passwords, and I knew that they were hashed in a database, and let's say I knew that the most common hashing algorithm was MD5, I wouldn't be able to reverse the passwords in the database, but I would instead be able to calculate the hashes for common passwords and compare those hashes against what's in the database. Right? So consider that I have a program that takes every single 3-length word, right? So every single word with 3 characters, it hashes it using the MD5. So let's say I've got MD5 of AAA, right? AAB, AAC, AAD, AAD, AAE, etc. And then I store all of these combinations inside of a table. So, yeah. Well, once I've done that, as an attacker, I now effectively have the reverse of all of the hashes of 3-character long strings. And it doesn't take that long, right? If you consider only letters, there's only 26 possibilities for each character. With numbers, 36. That's still not too long for a 3-character long string. I could generate this table in no time. And then once I generate the table, right, all I have to do is take the hashes inside of the database, put them through my table, and bam, I now have the password, right? So let's say that we create a new user, and the user is going to be Tom, and his password is going to be A. Right, so we've now created this new user. And now I'm an adversary. I somehow acquire this database and I learn about the hashes of these passwords. Now, just naively, I'm going to create a table of all hashes of passwords of one length using only letters, right? So A, B, C, D, E, etc. And then I'm going to put that in a table. I'm going to use a program to parse the password database, and then all of a sudden I can compare these hashes to what I have. So let's check for each letter. We're looking for the hashes 0CC175, right? Does this hash match? No. Does this hash match? No. Does this hash match? Yes. So now that I have the database, I know that the user Tom has the password hash 0CC175B9C, and the table that I've created indicates that that hash actually belongs to the letter A. So now I can log in as Tom, right? Because I now have the mapping between the hash and the actual password. And the database has the username in clear text. Usually this is the case so that we have a nice key system. We could also hash the username if we wanted to. But again, that would just be another table lookup. So once we do that, we've logged in, right? Notice that we never actually had anything that said this is Tom's password. We only had the hash version of the password, and then we actually happen to have a table that maps the hash to the letters. So storing these hashes seems like a good idea at first, but if you had a very powerful computer, you could actually create one of these tables that maps hash to a very long password. Now, keep in mind, to go into every possible password that's one length doesn't take long at all. Hashing functions are a little bit slow, so it takes a little bit of time, and it takes 26 times the time of the hashing function. However, when you start looking at strings of 2 length, right, that's 26 times 26 possible strings. Strings of 3 length, 26 times 26 times 26, right? Once you start getting into strings of 8, 9, 10, 16, right, you're getting into 26 to the 10, 26 to the 16 possible strings. And all of a sudden, generating this table is expensive, and storing the table is expensive because it may be gigabytes big. However, that's only a one-time effort. If you have a bunch of friends, we can pool together with all of our gaming PCs, we can build this table. And these tables are called rainbow tables. And I'm not going to tell you where to get them, but you can actually Google rainbow table and find websites where you can just download rainbow tables, which are simply mappings from hashes to the string they correspond to. So it's essentially a reverse lookup for hashes. Right? So now there's a huge problem. People are storing passwords as hashes inside of their database, and anybody with a rainbow table and the database can now crack passwords. Now, granted, you have to have the database with the password, or you have to have intercepted network traffic, which is nearly impossible these days because most password login forms use HTTPS, which actually encrypts the network traffic. So you won't be able to actually get the hash that's being transferred over the network. But if you do happen to obtain one of these password hashes, reversing it and getting the password is pretty easy because of the existence of rainbow tables. Now, how can users protect themselves? Well, since calculating rainbow tables is expensive, users with a high entropy, high length password can really stand a chance. For instance, the word password, right? It's 8 characters long, so it's decently long. Maybe it's in some hash, maybe it's in some rainbow tables, but it takes a little bit to calculate. So it's not in all the easy rainbow tables. However, the word is extremely common, right? You can kind of intelligently construct a rainbow table by using common words, or saying, yes, we're going to put password in the rainbow table, and we're also going to put password with the A replaced with a @ symbol, or the O replaced with a 0, because we intelligently know that these are the words that people might choose. You don't have to try every single combination. So the idea is to protect yourself, create a long password that would take a long time to guess inside of a rainbow table, and also make sure your password has high entropy, right? You don't want to just use one word because calculating the rainbow table for the English dictionary is not too challenging, right? However, if you have a string like, let's say I think an XKCD comic recommends 4 words, right? So like book, coffee, drinks, dinosaurs. Whoops. This is actually MD5. Right? So you've now created this password that is 4 plus 6 plus 5, 6 plus however long dinosaurs is, 4 plus 4 plus. Anyway, it's 16 characters or longer, right? So this is going to take a long time for a rainbow table to generate. And that means you're essentially safe. Now, there are some things that servers can do, or password store systems can do to further increase the randomness or the non-correlation between the hashes and the passwords. And we'll be getting to that in the next video, actually. So hopefully this opened your eyes to how to store passwords and how to, or the problems that could arise from that storage method. And hopefully this video was informative. Thanks for watching. Please remember to rate, comment, subscribe, and see you in the next video. Bye-bye.